Welcome back to another episode of Game Theory. We're still looking at repeated games. We just saw in the previous episode that if there is a unique Nash equilibrium in the game that's played once, then you'll keep playing that Nash equilibrium over and over again if the game is repeated a finite number of times. That result can be overturned if there are multiple Nash equilibria. So here's the idea. So it could be that one Nash equilibrium is better than the other, gives higher payoffs to one of the players. So what you can do is say to your opponent, if you cooperate, I'll play the good Nash equilibrium in the next round. If you don't cooperate, I'll punish you by playing the bad Nash equilibrium. So that can induce cooperation if there's a finite number of repetitions. So here's an example. So we'll have two players. Each one has three strategies. So we have A, B, and C, X, Y, and Z. This is a playing class where I'd ask who wants to be player one, but no one else is here in the room. Let's see, who are some of our usual volunteers? I think Megan volunteered once. Maybe more than once. And we also had sometimes Richard volunteers. So I'll have Megan and Richard. Hope you guys are okay with me using you in an example. So AX is going to be a payoff of 4 for each. And BY is going to be worse. And it'll be a bunch of 0 zeros. And let's say this game is going to be played twice. So first you got to analyze the one-shot game, the game that's played only once. So you do our usual best response analysis. So if Richard plays X, we can figure out what Megan's best response is. Megan's going to want to meet X with A, because getting 4 is better than getting 0 or -1. And if Richard plays Y, Megan's best response is B. Best response to Z is going to be C. Now let's do it the other way. If Megan is playing A, what is Richard's best response? We're just going to want to play X. Best response to B, that's going to be Y. And best response to C is going to be X. So you have two Nash equilibria. You have multiple equilibria, our condition we had here for potential cooperation. Now, cooperation can involve playing strategies that are not part of the one-shot Nash equilibrium. So here's what that could look like in this game. So Megan would really like to be at CZ, because C gets her a big payoff of 9, which is much, much higher than what she gets anywhere else. Now, unfortunately for Megan, CZ is not a Nash equilibrium, so the game is played only once, or the key players repeat the Nash equilibria multiple times. CZ is not going to happen. So is there any way in which Megan can induce Richard to play Z and have CZ happen once? It turns out that there is. So you can imagine the players can talk to each other. It's not actually necessary for communication for the purposes of a Nash equilibrium, but it's easier to think of it occurring that way. And you can think of a way that Megan can set up incentives using these equilibria to induce CZ in the first round. So we said that you can combine rewards and punishments. You can reward cooperation with the good equilibrium, AX, and punish defecting with the bad equilibrium, that'd be BY. So Megan's going to play C in round 1. She's going to announce that to Richard in advance. And she's hoping he's going to cooperate and play Z. So she says, if you go along with this plan, you play Z in the first round, then reward's going to play B. I'll play A in round 2. Now, the temptation that Richard's going to face is that if he knows Megan's going to play C, he might prefer to play X because playing X gives him a payoff of 1 instead of 0. So you have to have some way of punishing Richard for doing that. Megan does not like it when Richard plays X when she plays C because that gives Megan a negative payoff. So she says, if you play X in round 1, I'm going to play B in round 2. That's going to put us in the bad Nash equilibrium. And that's going to lower both players' payoffs. So after Megan makes that speech, Richard's got to calculate if it's worth it to cooperate or if instead he should just defect and follow his self-interest and play X in round 1 instead of Z. So cooperate is going to mean he's going to play Z in round 1 when Megan's playing C, so CZ in round 1. And then in round 2, Megan says she's going to play A to reward cooperation. So Richard will be responding by playing X. Richard's payoff from this will be, well, he's the calm player, so his payoffs always come second. He gets 0 in round 1, but then when AX happens in round 2, we're over here, so Richard gets a payoff of 4. So that's what happens when he cooperates. Let's instead look at what happens if he defects and does not go along with Megan's plan. Let's see, I'm running low on space here. Okay, if defects, that means Megan's already committed to playing C in round 1, but then if Richard just pursues his self-interest in round 1, he's going to play X and get a payoff of positive 1. Then in round 2, Megan punishes him by playing B, so Richard plays Y, and we're going to be over there. So Richard's payoff in that case will be he gets 1 in round 1 from playing CX and exploiting Megan's choice to play C. Then he gets punished in round 2 with BY, so he gets 2 in that case. So his total payoff from defecting is 3. Well, 3 is worse than 4, so Richard is better off from cooperating, so that means he's going to cooperate. So just to be formal, I'll write out what this particular Nash equilibrium is. So Megan says she's going to play C in round 1. And then in round 2, it's going to depend upon what Richard does. So A, if Richard plays Z, and if he doesn't cooperate, we're going to play B and punish him. Richard is going to play Z in round 1, and then X in round 2. So that's one example where you can get cooperation. So I'll stop the video here so my phone does not run out of memory again.